Where is he at? Where are you at? There he is. What's up,
Hi,
son?
everyone.
Hello, how's it going?
Hey, it is going good. Thank you guys for having me. I am a little bit sick. You might be able to hear it in my voice,
Oh
but I
no.
am super pumped for
That is
this.
dedication. That is
Sweet, sweet.
dedication. He could not let us hang. You couldn't leave us hanging, huh? You could have called in
No,
sick. You could have
Nah,
said,
he's
I can't do
dedicated.
it. No,
no,
He's
I gotta be.
dedicated.
not
That's
today,
right, he's
man.
right.
Not today. That's awesome. Well, dude, David and I are going to jump off. We'll be back with questions in 20, 25 minutes. So talk to you soon.
Sounds good. Will you be putting my slides? Okay, there it
No,
is.
should be up. Yeah.
There it is. Cool. All right. Hello, everyone. My name is Samyam Rajbhandari. I am a co-founder and the architect at the Microsoft DeepSpeed team. Many of you might already know what DeepSpeed is. Many of you might have trained your models using DeepSpeed. Today, I'll give a brief overview of DeepSpeed and walk you through some of our insights along the way as we developed DeepSpeed. Just some fun stories along the way, and also tell you about the key features of DeepSpeed. So at a high level, DeepSpeed is hi, you're back.
That wasn't so. We're improvising like a jazz band, basically.
Yeah,
Do you mind resizing the window that you're presenting with for the slides? Because it's a little bit vertical right now. And there we go. Boom. All right.
feel
I'll be
better.
yeah.
All right, all right, cool. Um, so DeepSpeed is a library for training, compression, and inference of DeepSpeed. We started by primarily focusing on model scale and speed. So let me tell you a little bit about what that means. We all know large language models have been blowing up. In the last 2 years, the size of the transformer models that were trained increased from a few 100 million parameters to hundreds of billions of parameters, about a 240 times increase in model size. During the same time, if you look at the AI hardware that these models are trained on, the memory capacity of these hardware only increased by 2.5 times. So how did we enable this massive increase in model size of these large language models? And that boils down to system capabilities. We built systems that allowed us to scale the model from a single device to hundreds and thousands of devices. And if you look at the trajectory of DeepSpeed in enabling large models, we enabled a 4,000 increase in model size in the same 2 year span where the transformer or the large language model size increased by 240x. Because of that, DeepSpeed has been used to train a lot of large language models that you see, including the Microsoft-Turing 17 billion, the Bloom Big Science model, Megatron-Turing 530B model, and so many more using some of the large model training technologies that I will share with you in just a moment. Now, in addition to model scale, DeepSpeed is super fast at training these large models. If we go back to the days where BERT was considered a large model, DeepSpeed had the world fastest BERT training time, where we were able to train the BERT in 44 minutes on a cluster of 1024 NVIDIA V100 GPUs. Fast forward now, we're able to train trillion parameter models on large GPU clusters. We can achieve near perfect linear scalability. What that means is as we increase the number of GPUs, your throughput or your training speed increases proportionally. There is very little efficiency loss. And we are able to do that on both older generation of hardware like the NVIDIA V100 GPUs or the newer generation of hardware like the NVIDIA A100 GPUs, all the way to thousands of GPUs. One of the challenges of large language model training is it's generally inaccessible because of just the size of the model and amount of resources required, or at least that used to be the case in the early days. If you look at the largest model you can train on a single device, something that a lot of data scientists have access to. You are limited to a couple of billion parameters. You cannot fine-tune something like Llama 65 billion. Um, so in order to make it more accessible, we developed technologies like ZeRO-Infinity, which allows you to leverage heterogeneous memory, things like CPU memory, NVMe, to increase the model size that you can train. And by using this, you're able to fine-tune models like Llama 65B or even a trillion parameter model with a single GPU if you have enough NVMe device. And that makes large language models a lot more accessible than if you needed a massive cluster to be able to do the same thing. We also develop technologies that reduces communication between devices when training large models. This is important because if the communication is slow, most of the time you're just spending doing the communication rather than any useful work. And that means you can only train these large language models on very powerful, very expensive supercomputing clusters. By reducing the communication volume, you make it more accessible where you can train it with much less bandwidth. So the model scale, speed, and democratization are kind of the three main emphasis points for DeepSpeed. So let me take you guys a little bit deeper into how some of these features were developed, some of the moments of insights where we were like, yeah, oh, this kind of works, and we built around that. So let me just take you back a little bit and share some of that. So early 2019, a couple of months before BERT had come out, and we were trying to train BERT at Microsoft. At that time, we already knew about distributed data parallel training, and NVIDIA Apex provided the infrastructure to do this. We didn't have DeepSpeed back then. We had access to 64 V100 GPUs, pretty decent GPUs at the time. But the problem was that this was a cloud cluster. The network on this machine was really, really slow, 4 gigabits per second Ethernet. To give you a reference, on today's supercomputing clusters, where a lot of these large language models are trained, that bandwidth is about 1600 gigabits per second, so roughly 400 times slower. And the memory wasn't too big either, so you could do a batch size of maybe 4 per GPU. And when we were training this model, it was incredibly slow. Training it on 64 GPUs was slower than training it on a single GPU, and we were just scratching our head, what is going on? Turns out we were spending all of our time doing the communication that I referred to earlier. Here's a simple loop of what that captures essentially what Apex was doing. We were using what is called gradient accumulation to increase the batch size, where you run with a small batch size, do a forward, backward, and you keep accumulating over the gradients. And then right before you accumulate, you do this gradient averaging across all the GPUs that you have, all 64 GPUs, every step after every forward and backward. And that was just killing time. We're just spending all our time just averaging gradients, averaging gradients. We were not making any progress. But once we saw this, we realized we could actually just move out the averaging part outside of the gradient accumulation. You let the forward and backward run for a couple of steps, just keep averaging on the local gradients on the same GPU. And once you're ready to update your model, that's when you can do the averaging across all the GPUs. It reduced the communication time by 16x. We were starting to see some scalability. Now the 64 GPU performance was no longer slower than a single GPU performance. And with that, we were able to train BERT in 8 days. No longer a super speedy BERT, but we managed to train it in a reasonable time frame. And that's where DeepScale was born. We used this to train a few early models inside Microsoft. And we were quite excited to get into this distributed training landscape. Then a couple of months later, new models started coming out. For example, OpenAI released a 1.5 billion parameter GPT-2 model. Megatron released 8.3 billion parameter Megatron model. And we were wondering, what can we do next? Can we train a larger, more powerful model? And what would it take to do something like that? The issue was that at that time, there were two forms of parallelism technologies that were used to train the model. Data parallelism, where you replicate all of your data across all of your GPUs, and you're limited by the single GPU memory. You can, again, scale to maybe a couple of billion parameters. And then model parallelism, which is how the Megatron models were trained, where you partition the model and you communicate all your activations throughout the training. And it incurs super high communication volume. The only way you can get around it is by having very fast communication, which was present inside a single node, what you call a DGX2 node from NVIDIA. But as soon as you go outside, the bandwidth wasn't there, and you can't really scale it further. So you were limited by the capacity of a single node, which was roughly about 20 billion parameters if you didn't care too much about running it efficiently. But we soon realized that the way data parallelism was trained, we were replicating everything, but we could actually not replicate everything. We could just have each GPU hold just a part of the model, and we can communicate them as they are needed. And if you did that, you significantly reduced the amount of memory required, but you didn't really incur a much larger communication overhead, nothing compared to the model parallelism, the tensor slicing that was done within the node. So that's where the whole zero line of idea was born. Zero redundancy optimizer. We don't redundantly store any optimizer model states across GPUs. So with that, it opened up the possibility to train models with hundreds of billions or even trillions of parameters without losing compute efficiency. And it was really easy to use. And so using Zero and the model parallelism, we at that time trained Megatron-Turing 17 billion. It was the largest language model at the time. And we were really excited about this Zero technology. We wanted to bring this out to the community and see what the community did with it. So we wanted to open source DeepScale, but interesting story, DeepScale was already taken as a name. So after brainstorming for quite a bit, we decided to change the name from DeepScale to DeepSpeed, and we open sourced Zero and DeepSpeed in 2020. And since then, Zero has been used as part of DeepSpeed library to train several large language models. It has been adopted to several frameworks, including PyTorch itself. And we were at the time a little bit upset that we had to change the name. But a couple of weeks down the line, one of my colleagues' daughter, she noticed that DeepSpeed is the same when you spell it forward or backward. And that was kind of cool. And we all started to enjoy the name a little bit more over time. And right now, I feel like it captures the essence of what we do a lot better than DeepScale. So we actually really like the name, and it's a palindrome. All right. So then we were starting to think, what is next? Around June 2020, OpenAI released a 175 billion parameter model. And we started to wonder, what would it take to train a trillion parameter model? We knew there were two possible paths. One is through Zero, and Zero has several different stages. Won't go into the details there, but we didn't have the full implementation of Zero at that point. But the other line of work that we had started to look into is 3D parallelism. Excuse me. 3D parallelism combines three different forms of parallelism: pipeline, model, and Zero. And the key here is the pipeline parallelism. Pipeline parallelism incurs very, very little communication overhead. So by using pipeline parallelism to scale across nodes, you can scale to really large models, and it is really, really efficient as well. The only kicker is that it is very complicated to both develop and use. But since we were planning to try to train a trillion parameter model at a very large scale, it made it worth it to try to develop a system where we are trying to get the best efficiency out of the system. So after a couple of months of work, we had our 3D parallelism ready, and we wanted to try it out. And luckily, we had, I remember this one weekend where one of the large GPU clusters, at this time, we already started getting supercomputing clusters inside Microsoft. And one of these clusters was going through an upgrade. And we had an agreement that after the upgrade, they would lend us the entire GPU clusters with over 1,000 GPUs for about 2 days to test scalability. So we had to, if we were going to test a trillion parameter, this was our window, and we had to make it work. Long story short, we managed to, during this weekend, schedule a job with over a trillion parameters. We submitted it, we waited for 30 minutes, and we got the first iteration time, meaning it was running. And during that weekend, we were able to produce this graph, which shows how the 3D parallelism technology can scale to a trillion parameter model with perfectly near scalability on 800 V100 GPUs. So with this technology, we collaborated with NVIDIA, and we used it to train Megatron-Turing 530 billion parameter models. This was done in about 2 months using 2,000 A100 GPUs. And then we used the same technology to also collaborate with the community to train Bloom 176 billion parameter model. Okay, so it wasn't quite a trillion parameters, but we know we could train trillion, and we were training models that were 500 billion parameters. So that was quite exciting. But then the question is, what next? Can we continue scaling the size of the model even further? Well, the problem is that the Megatron-Turing 530B, it took 2 months to train on 2,000 GPUs, and we only trained it on under 300 billion tokens. From today's standards, that's heavily undertrained. Today, the Llama 65 billion, a model that's almost 10 times smaller, is trained with over 1.2 trillion tokens, and even the MPT 7 billion is trained with about 1 trillion tokens. If you use the same kind of scaling laws and try to train a 500 billion or 1 trillion parameter model using 1 trillion token, it would take 6 months to a year on 2,000 GPUs. And if we did the scaling properly and trained it with 10 trillion tokens, which is probably about the number of tokens that would actually be needed to train this model to its full potential, it will take 10 years. It is no longer feasible to train these massive, dense models. So what do we do then? We can actually now scale with sparsity using mixture of expert models. What does that mean? An analogy that helps me think through this is when you're going to a hospital for a diagnosis or to a clinic, you don't go see every single doctor and combine what they had to say to get your diagnosis. You go to an expert based on your symptoms. Mixture of expert is kind of similar to that. You might have a really large model, but you will only use a subset of the parameters in the model based on the input token that is going through the model. And so here's a plot that shows a 1.3 billion parameter dense model loss curve during the training compared to a 1.3 billion with 128 experts. And then we compare that with a 6.7 billion parameter dense model. Excuse me. So here we're seeing that the 1.3 billion with 128 experts has a similar accuracy as a 6.7 billion parameter dense model. Now, if you were to compare the throughput, the 6.7 billion dense model is roughly 5 times slower than the expert model. And if you look at the total number of parameters on the expert model, it's actually 52 billion parameters because you have all those experts. So now you can scale to a really large model, but also run it fairly cheaply. So in order to enable this, we released DeepSpeed-MII for training, which allows you to train multi-trillion parameter MOE models with excellent training efficiency at the cost of training a much smaller dense model. So far we've been talking about just pushing the size of the models, right? But as we start increasing the size of the models, you would need larger and larger GPU clusters to fit the model. So for example, if we had to fine tune a 175 billion parameter GPT-3 model, that's going to take 256 V100 GPUs. It is a large GPU cluster that very few people have access to. But if we actually look at the modern hardware, the limitation is because we're trying to fit the entire model in GPU memory, But if you look at the CPU and NVMe storage, there's actually a lot more. The GPU memory is less than 50 times the overall storage in a system. And so if we could leverage the GPU, CPU, and NVMe memory, you could easily fit a trillion parameter model for fine-tuning on a single DGX2 node. And that would make large models a lot more accessible. The catch here is that those forms of memories are much slower. So NVMe, for example, is 60 times slower than the GPU memory. And even worse, in order to use these forms of memory, you would need to bring the data from these slower memories to GPU memory through the PCIe link, and that becomes your bottleneck. And that link is over 100 times slower than GPU memory. So what do we do? So I actually remember when we had the aha moment on how we can fix this. This was back in 2020. I was we had rented a cabin with a bunch of friends to celebrate my wife's birthday, and I remember I couldn't sleep because I couldn't stop this thought of data moving back and forth between NVMe and GPU memory. And there was this moment where I realized, well, the NVMe and PCIe links are really slow by itself, but if you could partition each parameters across all your GPUs and try to bring the data in from the slow memory, you actually have lots of these running in parallel, so you can get the aggregate bandwidth across all of these. And so we can now increase the bandwidth from something like 16 gigabytes or 30 gigabytes per second to hundreds of gigabytes per second. And this was the fundamental idea behind ZeRO-Infinity. We build upon it, and we release ZeRO-Infinity as part of DeepSpeed, and with it we can fine-tune models with hundreds of billions of parameters on a single GPU, eliminating the barrier to entry for a lot of data scientists for fine-tuning these large models. All right. So we mostly talked about training, but there are a few other things that we can do with DeepSpeed. For example, we can do compressed training. It allows you to train with really long sequence length using sparse attentions, or we have mechanisms like the progressive layer dropout, where instead of training through every single transformer layer of the model, you can selectively choose, just kind of like the expert of tokens, mixture of experts using your token, and a gating function to figure out which layers you want to go through and which you don't. And that can help you speed up your training. And of course, inference. Once you've trained these large models, you want to be able to inference them effectively at a low cost and productionize them. The challenge here is that the large model landscape is quite diverse. You have models that range from a few 100 million parameters to hundreds of billions of parameters. You have dense models, you have sparse models, and different scenarios have different requirements for inference. You might be doing a throughput-based scenario where you just care about cost. You don't care about latency. It's all offline, and you want to maximize your throughput. Or you might be doing a scenario where you're facing customers, where your latency is super critical, and you want to minimize latency. So at DeepSpeed, we developed a systematic composition of different optimizations such that you can get the best latency and throughput depending on the scenario across this entire model stack. However, the challenge is that there are lots of optimizations that goes into speeding up large language models. And from a data scientist perspective, it's not always clear what you want to do, even though some of the tools to do it might already be available, for example, DeepSpeed-Inference. So in order to address that, we developed a new library called DeepSpeed-MI2, DeepSpeed Model Implementations for Inference, where we've taken the popular open source model and applied DeepSpeed-Inference optimizations to them so that you can simply just, with a click of a button, run this model with the best latency and throughput. So here is a small code snippet on how you can deploy a model using DeepSpeed-MI2. You can pick your HuggingFace model that you want to deploy. You just say mi2.deploy, specify a bunch of things, and that's it. At the back end, DeepSpeed will apply all its optimizations, and you can get a handle on which you can submit your queries, and you can get really fast latencies and throughput. DeepSpeed-MI2 supports over 24,000 different models that are open sourced. At the time when we released it, it reduced the cost of inferencing Bloom 176 billion model by up to 40x, and it can also accelerate models like Stable Diffusion. Hello, am I running late?
No, you're good. Sorry, it was my internet went out, and I wanted to make sure I was still working. Keep going, man. My bad for interrupting the flow.
Okay, no worries. Something else that is tied to DeepSpeed Inference that we are really excited about that we released pretty recently is DeepSpeed Chat. I'm sorry, guys. My throat is acting up a little bit. So DeepSpeed Chat is kind of this interesting project because training a chat model requires RLHF training. The RLHF training pipeline has both training components and inference components in it, and it is equally important to accelerate both training and inference. And this was the first time where we used all the techniques that we've developed on the training side, combined it with all the techniques we've developed on the inference side to accelerate RLHF training. And it allows you to train really large models for chat really fast, if that's what you want, or really cheaply if you don't care about low latency and all you care about is cost. Okay, so we've kind of covered several features inside DeepSpeed, several DeepSpeed offerings like the DeepSpeed-MI2 and the DeepSpeed Chat. However, all of these features do not mean much if they are very hard to use. And so at DeepSpeed, we greatly care about usability. The ZeRO line of technology makes it easy to scale your model with virtually no code change. You can go from 1.4 billion parameter to trillions of parameters by using DeepSpeed without any change to your code. And because of how easy it is to use, DeepSpeed has also been integrated into HuggingFace and PyTorch, and you can just enable the DeepSpeed backend by just changing your configs or using a different launcher without having to change anything in your code. DeepSpeed is also infrastructure agnostic. It supports Agile ML, Azure VMs, or if you want to bring your own hardware and run it there, it works there as well. Let me kind of share how you would apply DeepSpeed to your models. So normally in PyTorch, you would create a model. All you have to do is wrap your model inside the DeepSpeed engine, and you're ready to go. You specify a DeepSpeed configuration file where you specify all different kind of optimizations that you want for DeepSpeed to enable, and that is it. And we are very grateful, and we're very excited that the community has been growing, and we've seen a massive adoption of DeepSpeed. If you're using a large language model, there's a good chance that it was either trained with DeepSpeed or it was trained using one of the technologies that was developed by DeepSpeed. We had over 4 million plus installs since we released it. We have tons of unique contributors, and a lot of third parties depend on DeepSpeed for their for training their workload and inference. So it's been a great journey, and I am super grateful to be part of DeepSpeed and the DeepSpeed open source community. And that is all I have for you guys. We welcome contributions, and if you enjoyed this talk, please do like our repo for DeepSpeed. And thank you.
Wow. That was a great presentation. Thank you so much, Samyam. You really had a great pace. So I appreciate you coming here, even though you were sick. You did a great job. There are some questions, but before we get into the questions that were there, I had one question that as I was thinking about a lot of this stuff, DeepSpeed has had a lot of impact in the industry, so much to the point that you see ZeRO or ZeRO-like optimizations being implemented in other optimization libraries. Can you just tell us a little bit about how ZeRO differs from fully sharded data parallelism in PyTorch, or maybe the implementation in Colossal? Just anything that you can say about that.
Yeah, first, it's to me, it's really exciting to see something that was developed at DeepSpeed now being adopted at different places. At the core, the fundamental technology is the same. You partition your parameters, optimize the states, gradients, and then you do the collectives there. There are differences related to usability. I think last time I checked on PyTorch side, the fully distributed data parallelism, it is not fully automatic. You have to apply that somewhat recursively.
Understood. Okay.
There, I don't know if it has changed over time. We've also seen ZeRO being adopted at Colossal-AI. Initially, since DeepSpeed is an open source, most of the implementation came from DeepSpeed, but over time, I feel like they've added their own enhancements to it. One of the things that I recall, not for ZeRO, but for ZeRO-Offload and Infinity, they have this thing called Gemini, which is a smart memory management to allow for partial offloading, which helps in some corner cases as well. But I think fundamentally all of these are the same ZeRO technology. I might be biased, but so far I haven't seen an implementation which outperforms the one that we have in DeepSpeed. But it's still exciting to see the adoption, and a little competition is great.
Yeah, I think it's healthy to push the boundaries of the space. And one thing I also just want to say before we get into questions is I really loved how you thought about some of these things and came up with insights, and it like progressively built on top of each other. I think that's really awesome, and it's, I guess, encouraging for other people. Some of these innovations don't come out of the blue, right? Like it comes through progressive iterations on some of these things. So I really appreciate that. There are some questions I'd like to get to. People are very happy with this talk. Okay, see, I'm so sorry. I'm very bad at this. I see a few different ones. I see someone asking a question about dealing with failures. So is there any capabilities like or any fault tolerance baked into the DeepSpeed training mechanism, or is that something you have to do on your own?
We've talked about elasticity and fault tolerance, and it's been features on our wish list, but it's not something that is fully baked into DeepSpeed
Got
at
it.
the moment. However, it is definitely a pain point, especially when you're scaling to tens, hundreds, or thousands of GPUs. It is something that we incur regularly, especially with like node failures and
Yeah.
ECC errors. It's hard to tell which piece is broken and so on.
Yeah.
So one suggestion I have, though, and that we use a lot, is just a simple all reduce test. Before you start the training, you would just do an all reduce test to ensure that we're getting the bandwidth that we expect. And if not, something is wrong with your cluster. And then you start doing a binary search on which part of the cluster. It's something that is definitely automated, that can be automated.
Okay. That's good to know.
Yeah.
But I remember when we were talking before, you were telling me about what it was like being on call as you were developing some of these really large models and how painful it was, right? To have to wake up in the middle of the night and be like, oh my God, there's this failure. And I guess the pressure behind it because of how expensive these resources are. Like one thing I was really, I was thinking about is how expensive all of this research is because, you know, it's very hard to, you know, do some of these experiments. Also making it very hard to, you know, you want to make sure what you're doing works or that you expect it to work, because if not, you're just wasting time and money. So yeah, it was really great. Sorry, want to keep it moving, make sure I get to other people's questions. Someone asked something, if you could shed some light on speeding up the inference of an LLM, like let's say the 7 billion or 40 billion Falcon without considering quantization. So maybe that's a DeepSpeed M2 question.
Sure. So how you accelerate it really depends on whether you're trying to push for latency or throughput. If you're trying to push for latency, then you're usually running at a very small batch size. And at that point, you're limited in your performance by how fast you can read the parameters from the GPU memory. So all the optimization centers around getting the best possible memory bandwidth, saturating all of your SMs so that you're pulling from the HBM memory as quickly as possible. So that's at a high level what we would do. If you're trying to maximize for throughput, then you would try to use a really large batch size and get the compute cores to use as efficiently as possible.
Keep it compute bound. Love that. Thank you so much, Demetrius. Sorry, go ahead.
No, man, I'm just coming on here because sadly we got to keep it moving. I told you all my name is Ringo today. I'm keeping time like a clock, just keeping us cruising throughout the day. Samyam, this has been awesome. I really appreciate you coming on here. I know it's no small feat to get a talk pushed through the PR department at these gigantic companies. So I think you probably worked harder on that than you did on the actual talk itself, which we all appreciate. There's a ton of people that said how excited they were for your talk, and
That's awesome.
you did not disappoint, man. You did not at all. You came sick and everything, and we all appreciate that so much.
Yeah, thank you so much.
Thanks for having me.